In this lesson, we are going to be covering the other half of the type of waves. So this lesson is going to be all about electromagnetic waves. By the end of the lesson, you should be able to identify the different types of electromagnetic waves. You should be able to explain reflection, refraction, and diffraction. So what is an electromagnetic wave? Well, an electromagnetic wave does not require a medium to go through, but it can go through a medium. So it can go through space and it can go through here on Earth. And some examples of electromagnetic waves are radiation, TV and radio waves, X-rays, microwaves, lasers, energy from the sun, and visible light. So electromagnetic waves are considered transverse waves because they have some very similar characteristics to a transverse wave. So the picture I have here is what we call the electromagnetic spectrum. So it shows all the different types of electromagnetic waves in order of their wavelength. So it goes from the shortest wavelength to the longest wavelength, starting with gamma ray, going all the way to radio waves. And the first one we're going to talk about are radio waves. So radios and TVs pick up the waves using antenna and convert them to sound waves. So if when you were little you ever had those things that people used to call bunny ears on top of their TV to watch your Saturday cartoons, those were picking up any radio waves that were being sent out from the station to bring you the picture and sound on your TV every Saturday morning. And some other examples that use radio waves as well are MRI machines. They use short radio waves and a magnet to create an image of the inside of your body, avalanche beacons, heart rate monitors, and radar, or radio detection and ranging. Now they use LiDAR instead, but all of these things use radio waves. So here are some pictures of an MRI machine and kind of what pictures come out of an MRI machine. So if you look at the picture there, you can kind of see where the radio frequency coils are that give off the radio waves, and the magnet is inside the machine. And then if you're looking at the two pictures of the foot and the brain there, this is what the MRI will show. AM radio. So this is an amplitude modulation, is what AM stands for. And AM radios can receive signals from afar, but they can also interfere with each other. The AM radio waves also refract off the ionosphere. So if you look at the picture there, they don't go out into space. They hit a layer in our atmosphere and bounce back off, and that is what helps let them travel further and further. FM radio waves. FM stands for frequency modulation, and FM radios need to be close to the transmitter to receive a signal, and they have little to no interference, but they can only travel a maximum of 70 to 90 miles. So unlike the AM radio waves, FM radio waves do not refract off the ionosphere. So this is why they can only go 70 to 90 miles. They have little to no interference, which is a great thing for those of you that always listen to FM radio like myself. But a problem is that as you are driving, let's say you're going from here, Duluth, to South Dakota, you have to change the station you're listening to after a while because you're not going to pick up that signal anymore. So now this picture, it shows what an FM and an AM frequency wave look like. So the top picture is an unmodulated radio wave. This is what it looks like. This is without any tampering whatsoever. An AM radio wave, or the amplitude modulation, is what your AM station looks like. So it's not affecting the frequency of the wave, but it's affecting the amplitude. And remember, the amplitude is the height of the wave from the rest point. And an FM radio wave is also known as the frequency modulation. So it's affecting the frequency of the wave. So it's affecting how many waves pass through in a certain amount of time. And it doesn't always look the same. The frequency is always changing. Now let's talk about microwaves. Yeah, you're probably thinking about the microwave in your kitchen that you use to make your ramen or your hot chocolate or whatever. So yes, those do give off microwaves. They work because the water that's inside your food is vibrating due to the microwaves, and it heats it up. Some other examples of objects that do give off microwaves as well are your cell phones, if you've ever used a pager before, your wireless internet, Bluetooth, and the GPSs that you probably have in your cars, and you have them in your cell phones as well. So all of these things give off microwaves. Now let's talk about infrared rays. So these can feel the warmth of objects. So if you've ever watched a TV show where they're using a thermal camera, this is what they are using. They are using an object that spits out infrared rays to detect the heat in objects, so it can look through a building and see where people in the building are located. So other objects that use infrared rays are heat lamps, things you may have for your puppies or your chickens or whatever else you have. Thermograms, those are the thermal cameras that they use for TV shows and things like that. Night vision goggles. Your remotes for your TV, they have infrared. Another one is heat-seeking missiles. They use infrared. And weather satellites. They use infrared to detect temperature changes in the atmosphere. So here's some pictures of thermal cameras, and it's just showing the heat in different objects. Now let's talk about light waves. So these are electromagnetic waves that we can see. We call this visible light. It's the colors that you see around you right now. The color red has the longest wavelength, and the color violet has the shortest wavelength. So how do we even see color? Well, you guys already may know the answer to this, which is amazing. But in order to see color, we're seeing the wave of that color being refracted. So we're seeing that the color we see is the wavelength that's being bounced off of whatever object you're looking at. And the rest of the colors then are being absorbed. So in order to see white, we are seeing all of the colors in the rainbow being refracted, and we see them because the wavelength is bouncing off and it's going into our eyes. In order to see black, if you're looking at something black, that means all the wavelengths are being absorbed. So energy of light is proportional to its frequency. So if it has a high energy, it has a high frequency and a low wavelength. So looking at the electromagnetic spectrum here, we're talking about the light waves. So you're going to look at this visible portion right next to ultraviolet and infrared. We're looking at this. If you can see that pink is on the left and red is on the right. So red has a longer wavelength and a lower frequency and energy. And pink has a shorter wavelength, so it has a higher frequency and a higher energy. And that's kind of what this transverse wave at the bottom here is showing you. So the speed of light depends on the medium. As I said in the mechanical waves lesson, the speed of light in a vacuum, so in space, is 3.00 times 10 to the 8th, or 300 million meters per second. If it goes through water, the speed decreases to 2.23 times 10 to the 8th meters per second, or 223 million. Now, if it goes through glass, it decreases even more, and it's 1.97 times 10 to the 8th, or 197 million meters per second. So there is nothing in the universe that can travel faster than light. The speed of light is the fastest thing that we have and that we can see. And here's a fun fact for you. So if you run at the speed of light, you could travel around the Earth 7.5 times in 1 second. Wouldn't that be nice to travel at the speed of light? We could just get where we want to go by running or driving in 1 second. It wouldn't take all day to drive across the state or across the nation. We could just be there in an instant. So now let's talk about intensity of light. So intensity is the rate or the speed at which energy flows through a given area of space. So the power is equal to the photons per second. So the more photons that are hitting your eyeballs, the brighter the light seems to be. Photons are the light giving off particle. They're the light particle that is super tiny that we can't see. And the greater the distance from the source of the object, the lower the intensity seems to be. So if you're thinking about driving on a highway at night, think about if you're going one way and there's a car coming the other way with its headlights on, it doesn't seem too bad far away. It seems kind of dim. The closer they come, the brighter it gets, right? So you have more photons hitting your eyes the closer it comes, and it seems kind of bright. So that's all this is saying. So now let's talk about ultraviolet rays. So ultraviolet is used for sterilization and sanitization because it kills bacteria. Ultraviolet is something that can produce vitamin D in your body, which is why they always say it's good to go out and get some sunlight because it's good for you. Well, it is. It enables bone growth. But there is a downside to UV rays as well. They can cause skin cancer. So too much exposure can be a bad thing. So some other objects that give off UV rays are black lights and security images on money. So if you've ever, held a UV light, if you've ever gone into a store and you see the cashier hold a UV light up to a bill, they're looking for this band that's inside of the bill, and it's a different color band for each specific bill, and it also has the denomination on it. You can't see that under normal light, but that's another security to prevent people from making counterfeit bills. So here's a picture of ultraviolet rays that come off of the sun. There are 3 different types. You've got UVC, B, and A. And our atmosphere helps protect us from a lot of this UV ray. And as you can see, the UVC doesn't get very far through our atmosphere. It stops at the mesosphere and the ionosphere. UVB, some of it all gets through, but some of it stops at the stratosphere and there is some that comes to the ground. And UVA, this all comes to the ground, but as you can see, the intensity of those rays are very, very little. So it's enough to benefit us, but not harm us terribly. Now let's talk about X-rays. So these can go through most matter, and if they've ever shown you your X-ray, you can see that you can only see your bones in your teeth because they absorb the X-rays. So looking at your X-ray, or the X-ray I have in the background here of a bat, the light parts are where the X-ray is being absorbed. So it's anything you see on the X-ray, those are your bones. But too much exposure to X-rays can cause cancer. So whenever you're getting an X-ray, if you remember those heavy lead vests they give you, that's to protect you from any stray rays. It's to limit the amount of X-ray that is going into your body. Some other objects that X-rays are used in is inspecting welds and airport security. So if you've ever gone to an airport and you're going through security, those big things that they use to scan your bags and they're using X-ray machines because they're trying to make sure that you have nothing bad on you. You don't have any metal or anything like that that you aren't supposed to take into an airport. Now let's talk about gamma rays. So gamma rays can go through really thick things. They can pretty much go through anything. And gamma rays are also used as treatments for cancer because they can pretty much kill most cells. And gamma rays are also used in food irradiation to kill any pests that might be in your food. Now let's talk about changing wave directions. So there are 3 different ways a wave's direction can be changed. The first one is reflection. So this is when waves bounce off a surface. So if you've ever stood in front of a mirror, you had your flash on while you're taking a selfie, and all of a sudden you look at the picture and your whole face is blurred, or you can't even see it because the flash was bounced off into the camera. That is reflection. So if a surface is flat, the angle at which the wave hits the surface will be the same as which it leaves the surface. So the angle in is equal to the angle out. And this is what we call the law of reflection. So if you look at that picture, this is exactly what I was just saying. The angle in is equal to the angle out. So if you want to test this theory, go into your bathroom with a flashlight, turn off all the lights, and flash the flashlight into your mirror and see if it's reflecting at about the same distance that you're putting it in. Now the next one we're going to talk about is refraction. So this is where waves can bend. So looking at the picture there, you've got a pencil in water, and it looks like the pencil's broken because of the fact that it entered a different medium. And this happened because the speed changes. The speed is different in gas than it is in a liquid. And the amount of bending depends on the medium that it is going through. So this could be different if you froze this pencil into a thing of ice. The last one we're going to talk about is diffraction. So this is the bending of waves around an object. And the amount of bending depends on the size of the obstacle and the size of the waves. So large obstacles with small wavelengths is equal to a low diffraction. Small obstacles with large wavelengths is equal to a large diffraction. So if you look at the 2 pictures on the right there, the first picture is showing a small obstacle, and so you can kind of see, or it's showing a large obstacle, so you can kind of see that there's a low diffraction there. It's all kind of in the same area. The bottom picture is nope. The top picture is showing a small obstacle, and so the diffraction is kind of, and it's showing a large diffraction there. It's kind of diffracting all of the light waves. The bottom picture is showing a large obstacle, and it's got a low diffraction, so it's not bending all of the waves, but you can see it's changing the direction. So instead of going out in a circular motion, now it's going out in a parallel motion below the object. So now let's do just a little bit of recap on the information we learned. We know that electromagnetic waves can travel through space and a medium. We know there are 7 different types of electromagnetic waves. We've got radio waves, microwaves, infrared waves, light waves, ultraviolet waves, X-rays, and gamma rays. And we learned that there are 3 different ways a wave's direction can be changed. So we've got reflection, which the wave just bounces off the surface. We've got refraction, where the wave bends due to a change in medium and speed. And we've got diffraction, which is the bending of waves around an object. So this ends the lesson for today. Again, this was a lot of information to learn, so if you have any questions, shoot me an email, shoot me a text. I will either answer it through email, or we can set up a time for us to meet and I can explain it to you in person as well. Otherwise, have a great day.